Welcome to the fourth lecture on alkaloids, which is on nicotine. Today we will discuss on the nicotine, which belongs to class pyridine pyrrolidine. We will discuss about the occurrence, properties and uses, structure determination of nicotine, Pinner's observation, and finally the synthesis of nicotine. As you can see the structure of nicotine, it contains according to the classification, it contains two heterocyclic rings. One is the pyridine ring and the second, as you can see, it is a pyrrolidine ring containing methyl group and in this nitrogen, and the point of attachment of these two rings, as you can see here, pyridine, nitrogen is numbered as 1, 2 and 3, means third position of pyridine is joined to the 1, 2, second position of pyrrolidine. So the point of attachment is the third ring, third carbon of pyridine and the second carbon or the positions 2 of pyrrolidine nucleus. Nicotine is the most important and widely used tobacco alkaloid found in Nicotiana species. Though nicotine is present throughout the plant, but its highest concentration is present in the leaves. It is colorless, levorotatory liquid, but its salts are dextrorotatory. It becomes darkened and on exposure to air due to auto-oxidation. As you can see, due to auto-oxidation, it has changed its color, converting into brown. It is highly toxic and increases blood pressure due to constriction of blood vessels. 40% solution of nicotine sulfate is used as an insecticide. Coming on to the structure determination, which is based on chemical analysis. The first step of this analysis is the determination of molecular formula. Based on the elemental analysis and molecular weight determination, the molecular formula of nicotine is C10, H14 and 2. The next step is the double bond equivalence, which determines the degree of unsaturation present. It is given by the formula A minus B by 2 plus C by 2 plus 1, where A corresponds to the number of carbon atoms, which is 10, B corresponds to the number of hydrogen atoms, which is 14, and C corresponds to the nitrogen atoms, which is 2. Substituting the values of A, B and C in the equation, we get double bond equivalence equal to 5. The third step is the nature of nitrogen. As 2 nitrogen atoms are present, we have to determine whether it is primary, secondary or tertiary. Nicotine forms dimethiodide with 2 molecules of methyl iodide. Means 2 molecules of methyl iodide are consumed. This means that the one molecule of methyl iodide has reacted on one nitrogen and the other one on the other nitrogen atom, which means that both the nitrogen atoms are tertiary in nature. That's why consuming only 2 molecules of methyl iodide, it converts into a quaternary salt. Next step is the oxidation, which determines the carbon skeleton present in the nicotine. On oxidation with potassium dichromate in the presence of sulfuric acid or KMNO4 or concentrated nitric acid, nicotine converts into nicotinic acid. Nicotinic acid contains a carboxylic group on pyridine at position 3. The important conclusions which can be drawn from this reaction is that nicotine contains a pyridine nucleus. Second, a side chain is present at position 3, which has been oxidized to carboxylic group. You can see the side chain which comprises of C5H10N. It is present at position 3. Third position, pyridine ring accounts for 4 double bond equivalents. As you can see, 3 double bonds and one ring, it corresponds to double bond equivalence equal to 4. Thus we have accounted for 4 double bond equivalence in nicotine. One double bond equivalent is still left. Next we come to the nature of side chain. Nicotine on reduction with sodium in ethanol, it converts into nicotine hexahydride. That means side chain is saturated and so it must be cyclic. As you can see, the pyridine nucleus is present. It consumes 6 hydrogen. Only 6 hydrogen atoms are consumed. 3 double bonds are present in pyridine. That means 6 hydrogen are consumed for the saturation of this pyridine ring. And an important conclusion which can be drawn is that the side chain does not contain any unsaturation. And it is also cyclic because one double bond equivalence is left. So as the side chain is saturated, this means it should be a cyclic structure according to double bond equivalence. Thus we have accounted for the 5 double bond equivalence which is present in nicotine. Next we come to the presence of N-methyl group. Heating nicotine with HI at 150 degrees centigrade and under pressure, it converts into methyl iodide. One molecule of methyl iodide is obtained, which on reaction with silver nitrate in the presence of ethanol, it precipitates out into AgI. Determining a quantitative estimation of this silver iodide reveals the presence of one methyl group in nicotine. This method is known as Herzig-Meyer's method. This means that N-methyl group is present in side chain. So we can rewrite the formula of nicotine as the pyridine ring. Third position side chain is present which is saturated, and C4H7 and CH3. This N-methyl group is present in nicotine according to Herzig-Meyer method. Next we come to the nature of side chain. Oxidation of nicotine with mild oxidant yielded nicotyrene. Its formula is C10H10N2, whereas the formula of nicotine is C10H14N2. The conclusion drawn from this reaction is that the absence of piperidine ring in nucleus. This means that this pyridine ring is present in nicotine and there is no saturated ring is present in nicotine. And you can see the oxidation of silver or oxidation with silver oxide. This as the pyrrolidine ring is present, it converted into an unsaturated ring on oxidation. This means that there is no piperidine ring in nicotine, only pyrrolidine or saturated ring, 5-membered ring is present. Next we come to the reaction with zinc chloride. Nicotine on reaction with zinc chloride, it forms an addition product which is known as nicotine zinc chloride, which on heating with soda lime, it forms pyridine, pyrrole and methylamine. The formation of these 3 products comes to the following conclusion. On the basis of these 3 products, we come to the following conclusions. First is the side chain is a pyrrole derivative, as we get a product as pyrrole ring. So the side chain is a pyrrole derivative. As the side chain is saturated, as we have already studied in the earlier reactions, and it contains N-methyl group also. These 2 conclusions we have already reached. It is N-methyl pyrrolidine. This means the side chain is present in the form of N-methyl pyrrolidine. So this is the side chain. This is the pyrrolidine and methyl pyrrolidine nucleus. The next point is what is the attachment of this side chain or the position of side chain. It can be attached with these, you can see in pyrrolidine, these two carbon atoms are equivalent and these two are also equivalent. This is known as the alpha position or second position, and this is the beta position or the third position. So the attachment can be from either from position 2 or position 3. Now let us see what is the position of this side chain. The following reaction gives important in conclusion for the position of side chain. Nicotine on treatment with methyl iodide gives nicotine isometh iodide, which on oxidation with potassium ferricyanide in the presence of sodium hydroxide, it gives nicotone. And nicotine on oxidation with chromic acid, it forms hygrinic acid. As you can see, this hygrinic acid, the structure of hygrinic acid is already known, and it contains a 5-membered ring and methyl pyrrolidine. It is N-methyl pyrrolidine nucleus, and the carboxylic group is present at position 2 or the alpha position. This means that the pyrrolidine unit is attached to the position 3 of the pyridine nucleus by means of alpha position or position 2. This is the position 2, which has been oxidized in the presence of chromic acid into a carboxylic group. So the pyridine, we already know the formation of pyridine carboxylic acid reveals the position 3 of pyridine, and now this hygrinic acid reveals the position 2 of the pyrrolidine ring, which is attached with the pyridine. Now the proposed structure of nicotine, as you can see, this is the pyridine nucleus, and the third position of pyridine, this pyrrolidine and methyl pyrrolidine nucleus is joined at position 2 or the alpha position. This is the proposed structure of nicotine. This structure is further verified by scientist Spinner. He, according to his observations, two evidences in favor of this proposed structure. The first observation, as you can see, we have taken the proposed structure of nicotine, which will justify the products obtained in this reaction. First, nicotine is treated with bromine in the presence of glacial acetic acid, and secondly with a sulfurous acid yielding dibromocotinine. This is the structure of dibromocotinine, which on further oxidation with a mixture of sulfurous and sulfuric acid, it degrades into 3 compounds. First is the 3-acetylpyridine, second is the oxalic acid, and third is the methylamine. By taking this structure, we can justify the following products. As you can see, the cleavage takes place from here. It converts into 3-acetylpyridine. Here methylamine is formed, and finally this degrades from here, converting into oxalic acid. Next observation of Spinner, second observation, a series of chemical reaction is as follows. We have again taken the proposed structure of nicotine, which justifies the degradation products of Spinner. Nicotine on treatment with bromine in the presence of HBr, it converts into dibromoticonine. The structure of dibromoticonine, as you can see, pyridine, and the third position, this pyrrolidine ring is attached, and here you can see bromo derivative, OH, double bond, and methyl. On treatment of dibromoticonine with barium hydroxide, it forms 3 products: nicotinic acid, malonic acid, 3 carbon, and one is the methylamine. As you can see, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. This is the 5-membered ring. which justifies the following. Nicotinic acid is formed when cleavage takes place from here. Methylamine is formed and the cleavage takes place in the presence of barium hydroxide, yielding a 3-membered malonic acid. Thus, the two observations of Pinner justifies the structure of nicotine. Finally, the structure has been confirmed by the synthesis, which was given by Spath in the year 1928. Spath took ethyl nicotinate. As you can see, it is pyridine and a ester group is present. Here it is known as ethyl nicotinate, and the second molecule was second reactant which has been taken as N-methylpyrrolidine. In the presence of sodium ethoxide, Claisen condensation takes place, resulting in the formation of this compound, which on reaction with HCl at 130 degrees centigrade, it converts into beta keto acid. Ring opening takes place and converting it into a beta keto acid, which on heating undergoes decarboxylation. As you can see, decarboxylation, this gross carbon dioxide is removed, converting it into this compound, and then on treatment with zinc dust in the presence of ethanol and sodium hydroxide, this ketonic group is converted into secondary alcoholic group, as you can see, which on reaction with HI at 100 degrees centigrades, this convert into the corresponding iodide. OH is replaced by iodine, and which on further reaction with sodium hydroxide and it converts into nicotine, which is a racemic mixture, which is further resolved. Thus, this is the Spath synthesis which was given in 1928. Thank you.